In this video, we'll take a look at the remainder theorem and the factor theorem. So we'll start with the remainder theorem. So from last day, let's remember that f of x, the polynomial function, is equal to the divisor function times the quotient function plus the remainder. And when we did specifically synthetic division, the d of x was a binomial function and was written x minus a. Well, if f of x is equal to x minus a times q of x plus r, and we evaluate this at that 0 point, what we end up getting is f of a is equal to a minus a times q of a plus r. But that means f of a is equal to 0 times q of a plus r, and f of a is really just equal to r. Well, that's a real shortcut actually, because if we can just evaluate the function at a certain point and we get the remainder, then we can save ourselves a whole lot of time if all we want to do is calculate the remainder. And we can put this as a theorem, so I'll just create myself a little bit of space here, and in this red box, let's put the theorem down. If you take a polynomial p of x and you divide it by a binomial x minus a, the remainder that you get is equivalent to that original polynomial function evaluated when x is a, or p of a. Let's take a look at an example. And in this example, we'll see if we can find the remainder when 2x squared plus 3x minus 5 gets divided by the polynomial function x minus 3. And so x minus 3 tells you that, well, if we thought about this as a minus 3, that means that a is 3. And so I should just be able to take the polynomial function, and instead of using x, I use a is equal to 3. And substitute it in. So p of 3 would be equal to 2 times 3 squared plus 3 times 3 minus 5. And that's equal to 2 times 9 plus 9 minus 5, which is 18 plus 9 minus 5, which is 9 take away 5. 27 take away 5, or 22. And we can double check and make sure this works simply by doing synthetic division. So my root would have been 3. Possible root, or my binomial number, would be 3, and then I have 2, 3, minus 5, carry the 2 down, multiply, add, and you can see that the remainder is 22. It's actually a little bit faster to have just calculated 22 by plugging the 3 in. And this gets even truer, more true when you have a polynomial function that's maybe even a little bit more complicated, a higher degree one. Let's take a look at another example. Let's find the remainder when x to the 11th plus x cubed minus 1 gets divided by x plus 1. So a is minus 1, because x minus minus 1, there's your x minus a. So I put minus 1 over here if I were doing synthetic. But the quicker way would be just to say, okay, my polynomial function evaluated when it's minus 1 is minus 1 to the 11th plus minus 1 cubed minus 1. Minus 1 to the 11th, it's an odd power, and another odd power, and so my answer is negative 3. And again, way faster than doing synthetic division when all you want to do is find the remainder. Let's take a look at the factor theorem and how that works, and then we'll try and put them together a little bit here too. And the factor theorem is actually quite intuitive. Essentially, it says that if you take one of these polynomials and you divide it and you get a remainder of 0, then the original thing that you divided by is a factor. If a polynomial function is divided by x minus a and the remainder is 0, then this x minus a is actually a factor of your original polynomial function. Basically, if you take a polynomial function and you write it as x minus a, and then there's some quotient that's left over as a function, and this r value is equal to 0. Well, if the r value is equal to 0, then you're not really adding anything on the end here, and so you've just factored your polynomial function. So with that, we should be able to do a question like this. Is x minus 1 a factor of this polynomial function? Simply by saying, okay, well, our a value is 1. What's the polynomial function evaluated when a is 1? Well, it's 3 times 1 cubed minus 7 times 1 squared plus 3 times 1 plus 1. So that's 3 take away 7 plus 3 plus 1, which is 0. And that's the remainder by the remainder theorem. And by the factor theorem, since the remainder is 0, then yes, x minus 1 is a factor. We can take this even one step further. There's only certain numbers that are possible factors, and that is something called the rational root theorem, which looks a little confusing to start, but is actually pretty amazing and pretty quick to use. So let's take a look at that, and then that's it for these notes. So if we have a polynomial function that gets written as the polynomial function is a to the n, that's the leading coefficient, there's the leading term, and then you get the next one, and so on, all the way down to the degree 1 term, and then the constant term. If you have this kind of polynomial function, the rational root theorem states that all the possible zeros, all the possible roots, have to be of a certain form. And that specific form is p divided by q, and p equals all the factors of the constant term. And the constant term is a0, and q is all the factors of the leading coefficient, and that leading coefficient is a sub n. So what I really care about is the very first number of the polynomial, the number in front of x to the n, and the very last number of my polynomial as well. So we can use the factor theorem, the rational root theorem, and the remainder theorem all together to factor polynomials, and this is how we do that. So in this example, we want to factor f of x is equal to x to the 4th minus 10x cubed plus 29x squared minus 32x plus 12, which before this would be basically impossible to do. Let's put it all together and see if we can do this. So possible factors are of this form, p over q, and the p value is all of the factors of our last term. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6 goes in, and plus or minus 12. So 1 and 12, 2 and 6, 3 and 4, and then positive and negative of all of those. And the q values are all the factors of the first term, which are just plus or minus 1. And so altogether, because there's a 1 on the denominator, the denominator is not really even needed. I just get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. These are the possible factors. And what that means is these are the possible a values in our binomial that might work to factor it. And then what we have to do is guess and test each one to find out which ones actually do work. We know if they work if the remainder theorem equals 0. That's the factor theorem. So if you can plug one of these points in and you get the remainder of 0, then you know it's a factor. And we just do that again and again and again and again. So when you do this, start with the simplest values to substitute into your f of x or your p of x formula. Don't try by substituting 12 in, because 12 to the 4th minus 10 times 12, this gets very complicated. Start with the easiest numbers, 1. Now you have to get pretty good at doing this. 1 to the 4th is 1 minus 10 times 1 plus 29 times 1 minus 32 times 1 plus 12, and calculate what that is. Yippee for us, it's 0. That means x minus 1 is a factor. And so now you do need some synthetic division, with a 1 here and write down all our coefficients, 1, minus 10, 29, minus 32, and 12, and see what the synthetic division gets you. I'm going to do this by pausing the video and doing it quickly. Yippee! I got a remainder of 0. That's what I was hoping for. Now I can do sort of what I was working on yesterday, and I can know that my original function is equal to x minus 1, that was my binomial factor, times what's left over. And what's left over is x cubed minus 9x squared plus 20x minus 12. And now I try to factor x cubed minus 9x squared plus 20x minus 12. And the way that I do that is look for the possible factors. So again, I look for my new p over q. Well, p is still the same I had before, q is still the same I had before, so I'm going to try values in my list of plus minus 1, plus minus 2, so start with 1 again and see what happens. If you want to save yourself some time, just plug 1 in to all of these x values and see what you get. 1 minus 9 plus 20 minus 12. Does it work? Negative 8 plus 20 is positive 12 minus 12. Yay! 1 works again. So, synthetic division again. But now using 1, minus 9, 20, and 12, the coefficients of this part. I'll do it quickly again. We should get a remainder of 0. And we do. That means that my polynomial actually factors to x minus 1 and x minus 1 again, and this piece, which is x squared minus 8x plus 12. Now, I don't have to do synthetic division again. I just need to know how to factor this. And we learned how to factor that back in Math 10. So I get x minus 1 times x minus 1. I'll save myself by writing a squared. And from this unit, we know a little bit about what happens at x equals 1 when we look at it graphically. And I can factor this. It's x and x. I need two numbers that multiply to 12 and add to negative 8. And so 1 and 12, no, 2 and 6. Oh, 2 and 6. Negative 2 and negative 6. And now I have my polynomial in a beautiful factored form, and I can go and graph it. That's what we'll be practicing in class.